In this video, we continue with our integration technique. The next is known as integration by parts, which in some circles is also known as integration of products. Integration of products, you will notice if you look at the left-hand side of this equation, it's a product of U and dV. This video must be viewed in conjunction with the notes that were uploaded onto the Moodle site. On the first page of those notes, we very simply derived this particular formula, that the integral of U times dV is equal to U times V minus the integral of V du. And this is called, when we use this formula, integrating by parts, where U is a function of X and V is also a function of X. Now we are going to be presented by a particular integral that is composed of two functions that are multiplied, and we're going to arrange it in such a way we will allow one part to be equal to U, the other dV, and when that is chosen correctly, we then simply use the corresponding right-hand side. So the procedure would be, firstly, choose U from the integral that is given, choose a function that you allow equal to U, then you choose the other part of the product to be dV. Now, after you have chosen U of X, you then differentiate U of X. So you derive it. And dV, obviously you cannot derive, you integrate. So when applying and when using integration by parts, in the initial stage, we will be differentiating U and integrating dV. And then once we have that U and its derivative and the dV, the differential and its function V, we then substitute into the right-hand side of that equation. Now, generally, the problem would be to go through a process where you must choose the correct U. And that in many cases could be a trial and error. However, you could use a priority choice of U, which works in most cases. And what is your priority choice? First, look for a term that contains logarithms or ln. Then you allow that term to be equal to U. If there is no log terms, then you look for powers of X. Your X to the 1, your X squared, and so on. And if there's no ln terms and there's no powers of X, then you can go for your exponential terms. E to the X, etc. E to the X, and so on. Now, the best way to go through this is looking at different examples, and we're going to apply this procedure to the examples. Okay, our first one, the integral of the square root of X times ln of X dx. Now, I would suggest when you are approaching an integration, you look for the easier cases first. In other words, is it a standard integral? In this case, no. Could you use a u substitution? In this case, no. Then we look for integration by parts, which is a product. And surprisingly, it's actually easier to identify integration by parts. And there you have square root of x times ln of x, a product. Now, your priority is going to be this. Let's choose u. So we want to let u equal to which of those functions? Square root of x ln of x? Well, let's go to our priority choice. It says go for a log term first. So in this case, we're going to let u equal to ln of x. And what do we do with u immediately? We differentiate u du dx is equal to 1 over x. Therefore, cross multiply du is equal to 1 over x dx. So we've chosen ln x to be equal to u. Then the rest of the integrand, in other words, the other function, square root of x together with its differential dx, you allow that to be equal to dv. So you let dv equal to square root of x dx. Now, if we look at u, we have a u and we have its corresponding differential du. As far as v is concerned, we only have dv. We have the differential. So in order to find v, we need to do the opposite. In other words, we must integrate dv. And if we integrate the left-hand side, we must integrate the right-hand side. And I'm going to write that square root of x as x to the half immediately. Now the integral of dv, that gives me v. And the integral on the right-hand side, x to the half, we're going to add 1. Our half plus 1 is 3 over 2. Divide by 3 over 2, and that gives me 2 over 3. X to the power 3 over 2. Now we have all that required to substitute into our right-hand side. So let's write down the formula to see how it's applied. The formula says the integral of u dv is equal to u times v minus integral of v du. Below that, I'm going to write the problem itself into square root of x ln of x dx. And that's the left-hand side. Now, all I have to do is substitute all of these, which we have already worked out. So what is u? U is equal to ln of x. So that will be ln of x. What is v? There's my v here. Multiplied by 2/3. X to the power 3 over 2. Okay. Minus my integral. And what is v? Again, v is 2/3 x to the power 3 over 2. And now du, and there's my du here. So that will be multiplied by 1 over x d. So that's my working out. And there's my problem. Now all I have to do is simplify the right-hand side. Okay, not much that we can do here. That's 2/3 x to the power 3 over 2 ln of x. Now we get to the integral. I'm going to remove 2 over 3 outside the integral, the constant, and x to the power 3 over 2. So x to the power 3 over 2 times 1 over x. Well, that's x to the power 1. And there I'm going to subtract indices. 3 over 2 minus 1 gives me x to the power a half. So this will be x to the power half dx. Sorry, that was a dx. Now, once we have done that, Then all we have to do is work on this integral. Now I'm going to pause there because yes, this particular integral is very easy to work out. But that integral could be a U substitution. It could be an integration by parts again. It could be any other technique of integration. So look at that integral very carefully before you solve. Fortunately, in this particular problem, this will all remain the same. Minus 2/3, and this is simple. The integral of x to the half, add 1, divide by 3/2, plus my constant c, and then simplify that. I get 2/3 x to the power 3/2 ln of x minus divide by 3/2, multiplying by 2/3, I get 4/9 x to the power 3/2 plus my constant c, and there the integral is worked. It's solved. So there, in essence, is a sort of basic application of integration by parts and its corresponding formula. So just to revise and go through the procedure, identify which is u, the rest of it is dv, differentiate u, integrate dv, substitute into the formula, and then complete the problem. Next example. The more examples, the better. You get that understanding. Now, in this case, we can actually do this particular sum two ways. And the one is, and easier, is a tabular procedure. Now, does this work all the time? No. It only works when u is an integrable power of x. And what do I mean by an integrable power of x? Well, simple. Powers of x, x squared, x cubed, and so on. Because you can integrate that. Now, the procedure is very, very simple. What you do is form a simple table. U and our dx. The problem, you allow that to be equal to u, because that is a power of x, x squared. Therefore, the dv, or in this case, dx part, and the reason I wrote dx because we are integrating with respect to x, is cos x. The u we differentiate, and we continue differentiating until you get 0. So what's the derivative of x squared? 2x. What is the derivative of 2x? 2. What's the derivative of the constant 2? 0. So the u going down the table, we differentiate. The dx, again going down the table, we integrate. What is the integral of cos x? Sine of x. Remember, standard integrals, the integral of cos x dx is equal to sine of x. What is the integral of sine of x? Minus cos of x. So integral of cos is sine, integral of sine minus cos of x. The integral of minus cos x, I can put the minus down. Integral of cos x is sine of x. So that will be minus sine of x. Now, we connect diagonally across from the first function of u to the lower integral on the right hand side. In other words, we connect this way, x squared to sine of x. Oh, let me get that as straight if I can. So here you connect sine of x diagonally 2x to minus cos and 2 to minus sine. Of course, 0 is 0, so we'll leave that out. Then you apply the following, and this is a very procedural aspect of integration by parts. No proof, no derivation. So you simply have to follow. But once again, you can only apply it when u is an integral power of x. Now, the first diagonal, you make that sign positive, the next negative, and the following positive. In other words, alternate the signs. Now, what's the beauty part of this tabular procedure? Once you have done that, once you have integrated u, differentiated dx, and applied the signs, you will be able to write down the answer immediately. How do you get the answer? You simply multiply the first diagonal together with the signs. So the first diagonal will be x squared times sine of x, positive. So that's x squared sine of x. Now the next diagonal, 2x multiplied by negative cos x. So we must take those signs into consideration. So that will be a plus 2x cos x. And then the last product, 2 times positive times negative, will give me negative 2 sine of x plus my constancy. And what? That's it. That is your answer. In other words, this tabular procedure simplifies the lengthy integration by parts that we done in the first example. Does it work all the time? Not at all. If I notice that my u is a x squared or x cubed or x to the power 4, then I can do it. So just when we think, oh, this looks so nice and so easy, let's look at the next example. Integral arctan x dx. Now there's no tabular form. But even before we do this problem, I hope anyone watching this video right now is not being tempted. What am I talking about? The derivative as opposed to the integral. The derivative of arctan. Yes, we know that answer is 1 over 1 plus x squared. That means the integral of 1 over 1 plus x squared gives me arctan. You can go to the tables. But do you have an integral of arctan? Not at all. There's no standard form for integral of arctan of x. And this is the reason I'm actually doing this particular problem. Whenever you see an integral of a function such as this, arctan, arcsine, integral of ln of x2 as well, then you're going to apply integration by parts. Now you may say, well, There's no product. But you insert that product. You can make it 1 times arctan of x. And it's at this stage where you realize that, let's just go back. There's no log term, the priority choice. There's no powers of x. There's no exponential. We only have 1 and arctan of x. And this you're going to have to play. So for example, if you decide, look at this carefully. If you decide, well, let u equal to 1. What's the derivative? Exactly. That's not going to work. So then you're going to let u equal to arctan of x. And there we know what the derivative of arctan of x is. It's 1 over 1 plus x squared. So du is equal to 1 over 1 plus x squared dx. So I have the u. What about dv now? Well, dv can only be the rest of it. If arctan is u, that means dv is 1 and dx 1 dx. And integrate dv integral dx, therefore v is equal to x. Now I have the u, du, v and dv, therefore I can apply my integration by parts, integral of arctan of x dx. In other words, use my formula uv minus integral v du. I'm just going to put that up there. What's my u? Arctan x. What's my v? X. So I will just write x arctan x minus integral of v. And what is v? X. And what is du? 1 over 1 plus x squared dx. Let's simplify. X arctan of x minus integral of x over 1 plus x squared dx. Okay, we're almost there, except we need to work that integral out. What is the integral of x over 1 plus x squared dx? Follow the simplified sort of approach. In other words, is that a simple, straightforward, standard integral? No, it isn't. Then the next step of the techniques was u substitution. Is it a u substitution? Okay, it could be. It is. Because when I look at, and I'm going to bring a different color in here, when I look at 1 plus x squared, the derivative is 2x. So I have the correct x, but I don't have a 2. Now, in u substitution, we allowed 1 plus x squared to be equal to u, then we found its derivative. Now, I want you to watch this very carefully. I'm going to do this on the side. So if I have the integral of x over 1 plus x squared dx, and you let u equal to 1 plus x squared, du is equal to 2x dx, and then substitute and work it out. But watch what I'm going to do. I'm going to say, okay, there's the x and dx, there's the x, and there's dx. The only value missing from there is a 2. So I'm going to insert the 2 because I need the 2, but I can't just put the 2 in. I will compensate for it by multiplying by a half, by its inverse, because a half times 2 gives me 1. So I haven't really changed the integral at all. Now, why would I do this? Because look carefully now. That integral now becomes, if I let 1 plus x squared equal to u there, that will be u, and 2x dx is du. And that integral is a standard integral that's simply equal to ln of u. So in our case, this is going to be equal to x arctan x minus a half times the ln of which was my 1 plus x squared plus my constant c, and there you go, there's your answer. We could write this in another way, and maybe you should be familiar with this and remember that we can write that as the ln of the square root of 1 plus x squared plus c. Do you recall that? Where I can take that half to the index, and that half is the square root. Now, notice over here, this part that I did could actually be done mentally. You don't have to write that down. But if you prefer doing U substitution on the side, you may have to. So you will find with integrals, when you come across an integral, you may have to work out the integral again. And then return to the original problem, like we have done here. All right, let's go to the next one. Integral e to the x cos of x dx. Now what I've tried to do in this video is give you an example, at least one example of the types that you could possibly come across in integration by parts. Okay, we have the integral e to the x cos x dx, and I hope by now that you can see there's a product. Definitely can't be U substitution. So we're going to use integration by parts. So yeah, will be by parts. So we got U is equal to, let me write this over here rather. U is equal to e to the x, therefore du is equal to e to the x dx. Then dv is equal to cos x dx, therefore v, I don't have to write the integral on both sides, I can just write the integral of cos x dx, and that gives me sine of x. So this will be equal to, therefore the integral of e to the x cos of x dx is equal to uv minus integral v du. My u, e to the x sine of x minus integral, and what's my v? Sine of x times du e to the x. So this will be e to the x sine of x dx. Now what is going to happen? Because we need to now find that particular integral, the integral of e to the x sine of x. What is that? Did you guess what we have to do now? That's right. We have to apply integration by parts yet again. So what I will do at this stage, I'll call this equation, let's call it equation A. And I'll return to that equation A just now. So I'm going to take this integral here. I'm going to call it I. I'm going to work it out separately. And after I've worked out whatever I is, I'll then do a substitution back into A. So let's take I, which is the integral of e to the x sine of x dx. What do I have to do there? Again, I will have to do integration by parts. So I'm going to let u equal to e to the x, therefore du is equal to e to the x dx. And I'll let dv equal to sine of x dx, therefore v is equal to the integral of sine of x dx, which is negative cos of x. Now I will substitute into the formula uv, u times v will give me negative e to the x cos of x minus integral of v du, which will be minus cos of x times du e to the x dx. Simplify that wherever we can, minus e to the x cos of x plus the integral e to the x cos of x dx. Now that I have the value for I, take these terms here and substitute it back into equation A. Therefore, it's lengthy but necessary. You may find ways of simplifying, but then again, we would like to see all you're working out. So what is equation A? Equation A is e to the x sine of x minus, now this is my I part, and I've worked out that I is minus e to the x, it has it right here, cos of x plus the integral of e to the x cos of x dx, and that gives me e to the x sine of x plus e to the x cos of x minus integral e to the x cos of x dx. Now I must do what here? Oh no, another integration by parts? Well, I'm not going to, and I want you to look at that very carefully. Integral of e to the x cos of x dx. What is it? That's right. It's actually the problem itself. It's the question itself. So how is that going to help me? Well, on the left-hand side, this is integral e to the x cos of x dx. So we have this integral and that integral exactly the same. And we simply transpose that and simply add it like terms. When I transpose, that minus sign becomes a positive, and how many of those integrals will I have? I'll have two of those integrals. 2e to the x cos of x dx is equal to, of course, that will just stay the same. I'm not transposing these terms. And now, therefore, integral e to the x cos of x dx divided by 2 is the same as multiplying by a half, as a half times e to the x sine of x plus e to the x cos of x. A beautiful example where there's a number of factors to consider. There's nice interplay between algebra, differentiation, integration. It's a beautiful problem. That brings this lesson to an end.